Good morning, good afternoon, good evening from wherever you're joining us from. Welcome to the first of two WomenTechConnect Lunch and Learn Fundamental series. My name is Esther King from the Sarakunda Internet Exchange Point. It is my pleasure to be your moderator for this series today. We appreciate that you have taken time during your lunch breaks to join us today. We hope you would learn today as we have lined up to be a fruitful and engaging session. At this point, would like to thank AfPIF for allowing us to be part of their virtual pairing series. As I mentioned earlier, we'll be having a great session today to be led by Michelle Opiyo, who's a senior network engineer from WomenTechConnect Communications, and she'll be talking on server provider essentials. She'll be covering all you need to know about BGP, MPLS, VPNs, and so much more. Michelle will be taking you through the fundamentals of routing, including key concepts of routing basics and some critical use cases during her career. Now the fun part, we also have a fantastic opportunity to win a LINX Slate course, and which is worth £2,000. And do not worry if you do not win this time, because there'll be another opportunity to do so at our next session next week. Alex from SNT will be joining us at the end of the session to explain more. I'd like to remind all of you that this is a Zoom meeting and it is being recorded. If you are happy to, you can turn on your camera and smile or wave. You will have a chance to ask questions to our speaker today, to Michelle. And because there are quite a number of us, we'll kindly ask you to raise your virtual hand, which is at the bottom of your reaction tab. And we will invite you to unmute yourself, introduce yourself, and then you can go ahead and ask your question. However, if you prefer, you can type your question in the chat box and we'll be monitoring that, and you can ask your question directly to Michelle from there. Before we jump into the session, we'd like to remember a special gem we lost earlier this year in our industry. And to help us celebrate her life, I'd like to introduce Jezebel Gilmore, a close friend, co-founder, and chief commercial officer for Packet Fabrics. And joining her is Victoria Foney, Susan's daughter. Jezebel, you're welcome.
Good morning, ladies. I hope that you have a fantastic session today. And I want to today talk about my dear friend, Susan Forney, and share a little bit about what I know of her and how she has contributed to our community. But most of all, I want to encourage you, every one of us, to follow in her footsteps and to give back to the community the way she has in her honor, so that we can continue to grow women in tech and this wonderful internet community that we have. But for those of you who knew Susan, she is as outgoing and courageous as anyone that you could imagine. She is a pioneer, and she spoke globally about the things that she's passionate about, which involved networking and women in technology. She didn't, however, start her career as a network engineer. She started, after she had graduated from school, with a journalism degree, she had joined Boeing and started as a tech writer. While she was a tech writer, she took everything she was supposed to be writing apart and learned everything, every little detail about everything that she's supposed to write about. As she was writing, she realized, and as what she was learning and interviewing the engineers, she realized that she knew more and about the things that she was writing about as she was learning them. And she decided that she can also be an engineer because they were contributing more and she was more than capable in those roles. So I want every one of you to think about this for a second. If you had a dream and you're in a role and you thought, well, I could do that as well, don't let your fear hold you back. She was fearless. She thought anything she put her thought to, she took up and became successful at it. I think that if you had known her, she would have said to you, and you asked her, should I be doing this? And her answer would be, why not? Give it a try. You could be fantastic at it. And if you made a blunder, which most of us do, she, only in her voice, would say, oh, honey, and came as close as possible to whether that you thought you needed help or not, to help you out in the way that you didn't think that you needed help, and helped you to be successful. So in her footsteps, I would like to ask you to do 3 things that she truly believed in. 1, be present, be there for yourself, and do not let what other people's perception of you get in the way of who you're trying to be. And 2, be action oriented. Don't just think about it, because thought, although great, is not useful if you don't take action to it. So if you felt that you're going to do something and you thought you've been thinking about it, and God knows that I have been thinking about a lot of things and that I haven't taken actions on, and now Susan's gone, such as that we thought that we were going to go apple picking together this fall. Now I can't. And I wish that I had done that earlier. So make the time and do the things that's important to you, and don't wait, because we may not have tomorrow. And 3, which is the most important, you are your own worst enemy. Your fear is your own worst enemy. Don't let your fear get in the way of becoming the best version of yourself, because Susan never did, even though that we both were extremely afraid of public speaking and did not find that comforting or something that we enjoyed. We pushed ourselves in support of women in technology, of our own career path, and wanting to make sure that we set a good example. So here I am talking to you, probably not very comfortable in my own skin at the moment, but Susan would have wanted that for all of us. And whether you knew her or not, she wanted you to have the best version of yourself. So with that said, please, in honor of our friend who's done an incredible job in supporting women in technology and our internet community, take the time, remember her today, and honor her today by doing something great for yourself and for others. So let me introduce Victoria Forney, Susan's daughter. Victoria is a fearless young woman herself. She is currently at University of Santa Barbara studying, and she's the pride and joy of Susan, much smarter than any of us could be. Well, either Susan and I. And I'd like to give Victoria the microphone to talk about what she remembers of Susan and how we can honor Susan from her perspective.
Hello. I've never spoken at something like this before, but I've never been too much of a tech person myself. I can't speak much on my mom's professional career. I just know she had one and it was great, but I kind of knew her more personally. I'd like to say that our relationship grew pretty well from meeting her at the airport 20 years ago in SeaTac. But I just wanted to give the speech that I gave at her service a couple weeks ago, because I know a lot of people couldn't make it out even if they wanted to. And I feel like, as her daughter, I probably want to speak on her a little bit personally. And that's probably the most personal thing I can say about her. So I'll just go ahead. I know my mom, when I was growing up, had to endure a lot. She moved across the country away from people that she had known her entire life at an age when most people are well settled, and started fresh over here in Boston, a place that neither of us had ever been before. She did this in a tough relationship and while basically having to raise me alone. We talked about this time a couple months ago, and I said how hard everything had been. And she said that she never felt like it was too bad because she always had me on her team. She said when we moved here together, we became a little team and we could have handled anything. And she was right. We handled a lot together. She was my only family and my only friend here for a really long time. Looking back, I see how strong she was on her own and how much she sacrificed to try and make the best decisions for me. She was brave, driven, smart, intensely herself, and I know I'll never find a better partner. She had been my designated person for a while before I moved here. When I was younger, I never wanted to be away from her side. She used to pick me up at KinderCare in her long blue raincoat, and I would run underneath the train to hide in her legs and waddle to the car. I would only eat a meal if it was in her lap. And I would write her letters at Nanog because I wanted to make sure she knew I was still thinking about her, but they never got delivered because I can't spell Albuquerque or any of the other places that you guys like to go. Despite our faults, though, and the fights and everything that comes with being so similar and so close to everyone, she never gave up on me. She had special high goals for me and the rest of everyone else, because she always saw the promise in people, even if we didn't see it at first. But ultimately, she just wanted everyone to be happy and safe, to have good lives, and to celebrate with us along the way. And I wish she could be here to keep celebrating, because there's so much she's going to miss. For the stuff she was able to be here for, there was nobody prouder. She was so proud and in love with everyone she met. Again, I've not met a lot of you guys, but I've heard a lot of your names a lot because she talked my ear off about it whenever she could, because she was just so into everyone in her life. And I'll love her forever. And I wish you could see how we're all doing.
Susan will sorely be missed. Okay. Now, Michelle is about to start. So, Michelle, over to you. We hope you're all excited as we are.
Thank you. That was very moving tribute from Jezebel and Victoria. Thank you for that. Yes, you're right. Susan will be sorely missed. She was very inspirational for real, for myself as well. She was very talented as an engineer and a very friendly one at that. So we'd like to continue to honor her by continuing to come together as women in tech and men allies as well, as we continue to grow the community and support one another as we work to make the internet better. So we'll jump right into it because we have quite a bit to cover. I'm not sure about the level of knowledge of the participants, so we're going to just go in from the fundamentals as we build up on the topics, and we'll kind of see where we get to. I know 1 hour and 15 minutes or so, I don't know, is a limited time to cover a vast topic, but we're going to do our best and see where we get to. So welcome again, everyone, and let's get started. Let me know if you can't hear me at any point, if I need to switch off my video, or if my connection gets messed up or anything. And as we mentioned, questions on the chat, or you could put up your hand. Feel free to interact, ask your questions. Don't be shy. This is a group of friends. So once again, welcome. Let me just quickly share my slides. So we're going to just dive right into it. And what we're going to talk about today is service provider networks, some routing fundamentals, just so we have a jumping off point as we continue to discuss the rest of the topic. Then, so we're going to look at the types of service provider networks. Then we're going to go into the routing fundamentals to see how all of these providers interconnect and come together. Then we're going to BGP, and hopefully we'll get to the MPLS section as well. So I'll just quickly start with like the classification of service providers. I did just a broad-based classification of the providers that we can find in the ecosystem. As we know, the internet is a network of networks. So it involves different networks interconnecting with one another to create the internet as we know it. So some of the providers that we have are access service providers. We have backbone service providers, transit service providers, content service providers, content delivery network providers, cloud providers, and mobile operators. So we'll just take a quick look a little bit into each of them. So for access service providers, these are typically providers who give the last mile connection to the user, right? So they're offering usually to residential or corporate customers, generally fixed or wireless. They could be giving, using technologies like FTTX, which is like fiber to the home or fiber to the business or fiber to the curb or whatever the case might be. XDSL, there's WiMAX for wireless communications. And we also have 3G, LTE technologies that are in use by access service providers. Generally, they'll provide some kind of customer premise equipment. Maybe they'll bring a router to your house or a switch or a modem that can be used to connect onto the internet. And obviously, their main purpose is to provide internet access to the users. Then we have backbone service providers. These are generally providers who give connectivity within a certain geographical area. So they could have their network, maybe it's within a metro in a certain city, or they could be national. They've built out their network. They have connectivity between various points across that region. So it could also be regional. So it could be, say, a Pan-African provider, and you've built out your network across Africa and connecting different countries and cities together. And you could also be a global backbone service provider, meaning you've extended your network to a large part of the world. So many backbone providers, a backbone provider can simply provide you with connectivity between those sites. A transit provider is also a type of backbone provider. Generally, they give internet access to the whole of the internet region. Generally, they have the full routing table within their network, and they allow traffic to flow from one network to another over their backbone network, right? So they are in particular reselling internet connectivity. Generally, they do a wholesale service, so they're trying to serve other providers who are in need of internet connectivity, and generally target like smaller ISPs than themselves who have maybe a smaller reach than they do. Maybe they want to serve content networks or CDNs or cloud providers and allow them to access these regions where they've built out into. So they're just some of the other providers that they would serve. Then we have content service providers. These are generally networks or providers who have direct relationships with their customers. So the customer doesn't have the concept of the intermediary network to get to them. They just know that I have a relationship with this particular content company that gives me some useful stuff on the internet. As we know, the internet is basically, it's the network of networks, but it's for people to use at the end of the day. It's about the users at the end of that pipe or network that you're building. So you have such companies, we have TV stations, we have video content providers, YouTube, Netflix, we have e-commerce websites, e-libraries, and they have different models that they use for their services. Some have subscriptions that you can use, some rely on ad revenue to run their networks and the like. And we'll see that some of these content service providers also have their own content delivery networks, right? But those are two different services. So let's look at content delivery networks. So content delivery networks are generally service providers that replicate some content that's available. Maybe ideally it would have been centralized, but they provide a service that allows the creator of this content or the owner of the content to decentralize it, right? And then distribute it closer to the customer. Now, this has the advantage of improving the customer's experience because it reduces the latency and improves the performance of the content that is being used and allows you to now get things like high quality video and images really quickly wherever you are. So some examples are Level 3, Cloudflare, Akamai. These are some of the content delivery networks that many people have come to rely on, AWS as well. Then you have Facebook and Google who have their own private content delivery networks because they have a large amount of content and they're able to then control how it's distributed to ensure that their users are getting the best experience from those from the content on their network. Then we have cloud service providers. These they offer various services that are running in their systems, which are based in their data centers, things like storage, database, compute, networking, software, and generally use like a pay-as-you-go model. This is a flexible model to use because it allows for the cost efficiency of relying on someone else's systems so that you don't have to build out on your own. So it's a very cost-effective method of running your operations, whatever they might be, whether it's banking or e-commerce or whatever the case might be. You will be able to host some of your data in their systems or in their data servers, data centers, and rely on that. So some of the services they offer, they have infrastructure as a service. Maybe you just want to have a server. Instead of buying your own metal, you'd utilize their infrastructure, such as servers, their operating systems, their network storage, their compute, or you could use a platform that they offer or software, such as Office, Mail, and all of that type of stuff. So those are cloud service providers. Then we have mobile network operators. I think everyone's familiar with this. We all have our cell phones. Hopefully they're smart. So they give voice, video, and data communications across a certain region. And normally they would require a certain amount of spectrum in order to do that. So the spectrum is normally given by the regulator or the government authority in whichever area that they're operating. And generally the spectrum has to meet the requirements for the technology you're deploying. So if you have 3G, you need to have spectrum that can support 3G or 4G or WiMAX or whatever the case might be. So in order for these service provider networks to actually be physically connected to one another, you do require some technologies that will allow you to connect your different POPs that you've created, locations where you are, to one another. So there's microwave that you can use. Like we said, there's spectrum you could use. There's some free bands that anyone can use and without having to pay a fee to a regulator. And there are also license bands that you can also get a license for so that it's exclusive to you. And then you can avoid things like interference, especially in areas where there's a lot of wireless deployments. There's also fiber optics, which is now the most popular method to interconnect networks or network points or points of presence or customers as well. that could be in the form of dark fiber, where a provider can get access to a pair of fiber that is not lit, so no one's going to manage it for you. You're able to put your optics at the end of that, and you make it part of your network and you utilize it as you please. There's also WDM, which allows you to use like a slice of the fiber, like a wavelength within that fiber, and use that to then have your connectivity between your sites. So you can lease a lambda from an operator who has his own large fiber network, say a backbone operator, and then you'll be able to interconnect your sites. So just a quick word on WDM. So DWDM is dense wave division multiplexing, which allows up to 96 wavelengths per fiber optic pair. Generally, it's quite costly due to you'll need additional equipment. So you're not going to just need your optical transceiver, but you'll also need other additional equipment in order to multiplex and demultiplex the wavelengths across the fibers. And it's generally more suitable for long distance transmission. And with the CWDM, this is coarse wave division multiplexing, which allows up to 18 wavelengths per fiber optic pair. So it's a larger size of a wavelength, larger spacing between the wavelengths, and it's more suitable for like your short distance, your pop links or your metro links within a particular region. So do we have any questions up to that?
I think you can proceed. There are no questions in the chat box at the moment.
All right, awesome. Cool. Just 1 sec, I just need to switch my slides. So we're just going to go over some routine basics, just so along you're able to follow along with the different topics that we'll be having. I'm using the slides that were they're originated and maintained by Philip Smith from a workshop that he ran with Cisco over the years, as well as having a lot of support from NSRC as well. Ideally, they're just open to use for learning purposes for workshops, and you can feel free to go over them anytime. You can get more details on the slides from BGP for all, in case you want to go deeper into it and have access to even more content for the purposes of learning and sharing. So we'll go over a couple of routing concepts quickly, starting with what is an actual router. So a router is a layer 3 device, which means it's able to understand IPs and it's able to interconnect networks at layer 3. So in order to be connected to another network, which is not within your control, the only way you'd be able to do that is via a router, okay? So generally what it does, it looks at the destination address in the IP packet and then decides how it's going to forward it. And how does it go about this? It will go and look into the routing table, and each router has its own routing table. So it will try and match the destination address of the packet it's received with the entries that it has on the routing table. Then if it sees a match, it's able to forward that to another router or possibly to the destination if it's connected to it. Then a default route is just a non-specific route, a non-specific destination that you'd forward your packets to, maybe onward to another router that would probably have the full routing table or more contents in its routing table to be able to determine how to best route or forward that traffic. So this is an example of a routing table. We have a couple of destinations. We have the next hop and we have an interface. So we say that a router is operating on layer 3. It's based on IPs. So we have our destination, for example, 10.40.0.0/16, and it has a next hop that's 192.248.40.60, and it says it goes out Ethernet 0. So once it receives, if this router were to receive a packet destined to this destination, it would look into its routing table, determine whether it exists, and it will find yes, it exists, and it will check the next hop and knows that for this next hop, all I have to do is forward this traffic out of Ethernet 0. and off that will go. So it's the same for the various networks that it's learned, and it will do so via various protocols, and we'll go into that shortly. So you can have more than one routing table. You can have more than one routing protocol running on your router at any given moment. However, most of the different routing protocols will allow you to only have one instance of them, right? So if you're using OSPF, you'll have only one process of OSPF running in that, although you can have other routing processes running at the same time. And then all the routes that are launched from all these different protocols will then be evaluated, and the very best of them will get into the global routing table, right? So all the protocols that exist in your router could learn routes, but only the very best, dependent on some particular metrics, will be selected to be in the global routing table of that particular device. So in most cases, you'll find that the decisions are updated periodically or as the topology changes, but that depends on what type of routing protocol you've done. And we'll get to that part. When a router is doing a route lookup, it's going to look for the best match. So it's not the first one that it sees that's close to the destination it's looking to. It's going to look for the very closest match to its destination and select that, okay? So we can take a quick look at an example here. We have a packet coming into router 2, and it has an IP address. The destination is 172.16.1.1. So router 2 receives this packet, and it then looks it up in its routing table. So it has a couple of entries in its routing table. We have 172.16.0.0/16, and then we have 172.16.1.0/24, and then 172.17.0.0/16, and 172.18.0.0/16. So we're looking for the closest match and the longest match to 172.16.1.1. So we already can eliminate a couple of this. So it's not 172.16, no, 172.17, and it's not 172.18. Those are not matching this particular packet. However, these two do, but 172.16.1.0/24 is the longest match. It's the most specific of them. And it says that this packet should then be forwarded to router 4. Okay, so then that packet will go out of router 2 and into onto router 4, which will also look it up on its routing table as well. Router 4 also has a routing table, and will try and check which exact interface should I forward this traffic out of. So every single router's decision is independent of one another. It's only based on the contents of their own particular routing table. If, for instance, router 4 didn't announce this route to router 2, router 2 would have made a different decision about where to forward this traffic to. It could easily have forwarded it out to router 3 because that was the best, longest match it would have in absence of router 4's announcement. All right. So that's just explaining what we've talked about now. All right, so routing, there's a difference between routing and forwarding. So routing is the process of building the maps and giving the directions of how we're going to move this traffic on from our network to the next destination. While forwarding is simply just pushing the packets through. Based on the directions that have already been given, the forwarding decision is simply to push the packets through the interfaces without having to look up the routing table. So IP forwarding. In IP forwarding, the router decides what interface to send the packet out to. Then the forwarding table, the routing table gives an input to the forwarding table. So all the forwarding table needs to know is what is the route, what is the next hop, and then it adds a couple of other fields like what's the MAC address of the outgoing interface, what's the outgoing interface. So once it receives a route that the router has already made a decision of how to route it out and says next hop is Ethernet 0. So the forwarding table will look at now all the information for Ethernet 0, so it can re-encapsulate the packet and be able to send it out. So it's going to do things like change the MAC address. It's going to change the source MAC address, but the destination MAC address will remain the same, right? Because you know that forwarding is on layer 2. So forwarding is done by specialized hardware. Routing happens in more like the software decision-making control plane of the router, and forwarding happens in hardware on specialized CPUs. So let's just take a look at what we were speaking about just now. We said we can have different routing tables that exist in our router. We have in this example BGP, which we're going to go into detail about later on. We have ISIS, we have OSPF, we have connected routes. Connected routes are like the IPs on the interfaces that exist on your router. So those are also considered as routes. And then there are static routes. Static routes are routes that you can define, the user can define manually into the router, and in order to cause them to enter the RIB, right? The routing table. So based on all this information received from these protocols, they're gathering information in different ways. We'll go into that. They will, then the very best of these routes will be selected to go into the routing information base, right? So all these protocols could also announce the same routes, but they would, one of them would end up being the best one because they have certain metrics that the routing information base will take into consideration when it's trying to decide which is the best route. Some are more trusted than others. The connected route is the most trusted of them all because it knows I'm definitely connected to this guy, so I'm definitely sending out this way. Static routes, those ones allow you to change the priority. So you could then decide how preferred you want a static route to be. OSPF and ISS have their own metric, which depends on the vendor, so it may vary. And then BGP also has its own metrics, and that may vary as well, depending on whether it's used internally within your ASN or externally. So the best routes are selected, and then based on this information, the forwarding information base is then created, which has the best routes and then includes, like I said, a few other details that are used for encapsulation, like the MAC address and all of that. The destination MAC address and that is required to send out the traffic. Right. I think we've covered that. So we talked a little about this. We discussed explicit versus default routing. There are two ways that you could route. You could either have a default route, let's say you simply connect to one provider. In that case, then it doesn't really matter if you had, say, the full routing table within your router, because all your decisions will lead to you going out of one interface, or maybe two, but you would be sending them out to the same provider, meaning that you don't really need to store the full routing table, because even if your router makes all those decisions, there's only one way out. So in that case, it makes sense to have like a default route, right? Also, default route is where you send the traffic if you don't have the specific route in your table. Then you could have an explicit route, which can be learned from different protocols, as we've seen. It's more complex because we said now it requires memory in your router to store all these routes. There's high overhead because we said the router has to go through every single entry within its routing table in order to determine, have I gotten the actual best path to my next destination? So in that sense, you'd need probably a bigger box if you're doing a full routing table, or the default free zone, as it's called, rather than if you're simply doing a default route, because in that case, you're not needing you don't need a lot of memory or CPU, or there's not much overhead related to using the default route. So what you want to do is probably, depending on where in the network, have a hybrid where you're using some defaults in some areas and having the full table in other areas so that you can make it as efficient as possible. So these are just some terms we're going to go over. Egress traffic. Egress traffic is how packets are leaving your network, right? So how does, what does that depend on? How packets leave your network depends on what routes have you received from other routers or other networks. Are you accepting those routes? Because someone could send you routes, you don't have to accept them. Then it depends also what's the policy and the tuning that you want to have. You might want to do some traffic engineering, meaning that even if I receive a particular announcement from a certain interface, I might not want to use it. Maybe it's connected to my expensive provider and I prefer to use another link, or maybe it has high latency, various factors that would cause a provider to tune or create policies on their network. Then also, like we said, peering and transit agreements. I think we'll go deeper into what peering and transit is, especially as we get to BGP, so don't worry too much about that. But it's still basically about the policy that you have on your network, which could be based on your business needs or your own network kind of situation. Then we have ingress traffic. Ingress traffic is how do packets get to your network, right? So this ingress traffic is based on what information you sent out. Have I announced that I am the owner of 164.20.0.0/24, right? Have I sent it out to the other networks? Have they accepted this announcement that I sent to them? That also affects whether I receive traffic from the particular interface I shared it out of, or session. So in order to understand this better, we're going to take a look at an autonomous system. An autonomous system, like we've talked about all these different service providers at the start of the presentation. So an autonomous system is a collection of networks that are under the same routing policy, and then in general, they're under a single ownership or trust or administrative control. So one network or entity is responsible for that particular set of devices and whatever makes up their network. So this is an example with AS100, which is made up of these 5 routers. All of these routers they're owned by whoever owns AS100 and they're within their administrative control. They're able to configure all of these routers and determine what the policy will be within this network, and also probably have a single IGP or internal routing protocol that they can use within that network. So a couple more terms we'll go over. So neighbors. Neighbors are directly exchanging routing information. There are two concepts of neighbors. In routing protocols, the network that the device that you connect to on the interface that you're connecting to, those are considered to be like neighbors. In BGP, your neighbor, the term for neighbor in BGP is like your peer, okay? So neighbors will exchange routing information directly. So 2 interfaces directly connected to one another, and you turn up a routing protocol between them, they'll be able to directly exchange information. You might require a few more tinkering and stuff to get it to work. They might need to have the same metrics configured on both interfaces exactly for them to come up. In some cases, it doesn't. So those are neighbors. Then announcing a route is sending some routing information to a neighbor. So this is simply telling a neighbor, hey, I have access to this particular network, say network 1, right? Then accepting is when you receive the information that you've been sent by your neighbor, and you use this information to calculate the best paths on your network. So you evaluate to see if it's a best path, which can then go into your global routing information base. Then originate is to insert the routing information into the assignment. So this normally happens, you originate networks in BGP, and we're going to see that in a bit. Cool. I think I need to speed this up. Yes, so we said that traffic flows in the opposite direction of the announcement. So if you announce some information to me, it means then my packets can flow in that direction back to you, okay? So in this case, we have AS1 and AS2. They're both announcing some routes to each other. In order for there to actually be connectivity between these two networks, AS1 must announce its networks to AS2, and AS2 must accept from AS1. Then AS2 must also announce the networks that it has behind it to AS1, and AS1 must accept them in order for there to be the two-way flow, right? Because otherwise AS1 might know about AS2 networks, so it would send the packet over. But once AS2's routers are trying to evaluate, okay, how do I send this back? They'll be unable to find it in the routing table and they might have to drop the packet. So like I said, every router makes its own independent decision along the way. So what about when you have multiple ASs, right? And it's a good example of probably how the internet works. So we have a couple of ASs here. We have AS1, we have AS34, AS8, and AS16. And what we're trying to do here is get between network 1. We want the devices or resources or users who are connected to network 1 to be able to access the users, devices, or resources on network 16. So what needs to happen here in between in order for this to be feasible? So we need AS1 first needs to announce N1 to its upstreams. It could announce them to both, to AS8 and AS34, or just one of them. And say it announces to both, then both of these networks should announce that same announcement that they received onto AS16. So that once traffic comes here, and then AS16 also has to accept it. So, and the same goes for AS16. It has to announce its network 16 to AS34 and AS8. One of them has to accept it and forward it on to AS1. So that once traffic flows, then we are able to get the full reachability, right? And remember that traffic flows in the opposite direction of the announcement. So if you announce it this way and I can reach it, then it means my traffic can flow back to you in the same way that I received it, hopefully. So what about routing policy? How do I then control how traffic goes out of my network or comes into my network? I think this is also a really important discussion to have, the concept of routing policy, because I see a lot of people get stuck on it, especially when it comes to the internet. You assume that just because I am announcing my prefixes, everyone is accepting them, and therefore traffic should flow how I see is fit. But remember that every network is autonomous. We said autonomous network, autonomous system. They will each make their own decision about how they want that traffic to flow, or how they want to receive their own traffic and how they want their traffic to go out of their network. So it's all networks making their own decisions. And in the end, it still generally works, but it might not work how everyone wants it to work. But you can control only a portion of it, right? Usually maybe the fast hop to your operators. You can control how maybe the traffic will flow back in that sense. So anyway, so routing policy is how it's used to control how the traffic will flow into your network and out of your network. So the network operator will make the decision on what routing information to accept or discard from its neighbors. It could be individual routes, it could be routes from a particular autonomous system, RAS, or it could be routes passing through a certain autonomous system or belonging to certain groupings. You could decide as you see fit. When you have your own network and you're running, say, BGP, you have a lot of flexibility, and that's one of the key things that BGP does. As we're going to see, it allows you to implement policy on your network. You don't simply take updates from everyone without any control. So it gives you a lot of control about how traffic flows to and from your network. All right, so let's look at some of the limitations like I mentioned. So here we have AS99, and the internet, which is a whole bunch of networks. And AS99 would like some traffic to flow in a particular direction. To like all the traffic, which is destined to red network, to flow on the red link. And all the traffic that's destined to the green network to flow on the green link. So let's see what they can do about it. So AS99, in order to implement this policy, right? So it will have to accept the prefixes of sent from the red network on the red link and deny probably those sent from the green network. Remember, it could also be receiving some of the green's network here, but all it has to do is make sure that it doesn't accept any other traffic except ensure that it accepts red's network information on the red link. And then green network information can be accepted on the green link. But like I said, the internet is made up of many networks. So in this case, we see that AS99 has an upstream provider, right? And this upstream provider also has their own network that they are operating and they have some policies for. So in order for AS99 to be successful, AS22 has to be cooperative as well with what AS99 would like the traffic to flow in. But it doesn't mean that the next network will make sure it only flows through the red link. So there's a zone of control. So between like two immediately controlled networks, there's opportunities for you to be able to force particular traffic on a particular link, because there are many tools that you can use in BGP. We'll look at that. That will allow you to say, I want my traffic from this network coming this way and from this network coming this way, based on some policy options that are available. So as of June 2021, we have 120,000 IPv6 prefixes on the global internet table and around 860,000 IPv4 prefixes, which are quite a number of prefixes, and it makes it very difficult for you to obviously come and individually decide what to do with each and every prefix when you're making a policy. So there are tools that you can use to tie maybe particular ASs or particular groupings of announcement together. But that's beyond the scope of this for now. Okay, so we know how routing works and how the routers are able to do what they're doing. So we just want to take a closer look at why routing protocols are useful to us, right? If we wanted to get the routes, say, to every single network out there, we would have to form a neighborship with every single network out there. But that's not really how the internet works, because that wouldn't be scalable. So we wouldn't have the internet we do as it is now. So what happens is that each network connects to the next and the next, and then they're able to eventually share all this information. And then every network is somehow interconnected without having to bear the cost of going to actually physically connect to every different network that exists in the world. Okay, so we want to talk about routing protocols, and what we want to ensure is that we have protocols that allow us to scale our network, which means we can grow our network, and we are able to connect to one another, and we're able to have the internet. So there are certain categories of routing protocols. We have interior gateway protocols, which are within your autonomous system. Remember, like we looked at AS100. So we have those that you'll use within the realm of your control. That's where it's safe to use them. Those are called interior gateway protocols, right? And they'll carry, generally they will, as a best practice, they should only carry information about your internal infrastructure. What's your internal infrastructure? These are things like your loopback addresses, your point-to-point links. Ideally, that should be pretty much it. And maybe a few internal services if you have them. But you want to just keep it very small, very limited, so that you're just addressing your infrastructure. How do I get from router 1 to router 2 to router 3 to router 4 within my network? That's all you want your IGP to be bothered with. So the commonly or widely used ones, at least in operators for service providers, is OSPF. and ISIS, which is intermediate system to intermediate system. OSPF is open shortest path fast, which are two fairly similar protocols. They both have the same idea of topology. It's just that ISIS doesn't really operate at layer 3. It's kind of layer 2 adjacent. And OSPF is in layer 3 fully. So that's the slight difference between them. But a lot of the other things you can do with them are pretty similar. So why do you want to limit the scope of this interior gateway protocol that you're choosing? You want to be able to limit your scope of failure so that, imagine if you are, okay, so you imagine your network, you have all your devices at your different ports and your different customer locations, etc. They don't tend to be the most resilient or reliable links. They do tend to fail from time to time. And you don't want that every time there's a change in your network, the whole network has to reconverge. It has to recalculate every single router. Remember that for IGPs, they have the same view of the network. So if a link goes down, all the routers within the network have to know that that link has gone down, and we need to all recalculate our best paths to various destinations, okay? So the reason you want to keep the number of prefixes low here is so that you can have a scalable network. If you have 1,000 routes, you're able to converge quickly and be able to make a routing decision in the right direction, rather than causing, say, something like a routing loop, because every router hasn't finished updating its routing table. So you want to keep it small and you want to keep it efficient. Then what's an exterior gateway? EGP is an exterior gateway protocol. What is it used for? It's generally used to convey routing information across autonomous systems. So this is separate from your IGP. Your IGP is running independently, feeding its routes into the global routing table. And then your EGP is running independently and feeding its best paths into your global routing table. So there's only one EGP currently. It's only BGP. It's always been BGP version 4 for a very long time. And it seems that it will continue to be that way for a while. So why do we need an EGP? Like we said, we want to be able to scale our network. Now, BGP is designed to be scalable in the sense of it can handle all this. We have 820,000 routes or more on the global internet right now. Yet BGP is still able to handle that large number of routes because of its design and its updates, how it runs its updates and all of that. It allows it to then be able to manage changes in the global routing table in a more stable manner, as opposed to an IGP. IGPs are very chatty. They want to know, are you up? Are you up? Are you up? Are these routes still good? Are they still good? Are they still good? So they're very, very chatty. So BGP is much less chatty, and it'll send updates as appropriate. And even while some of them might take time to propagate, it's usually not very detrimental to the operation of the internet. And especially in the case where you would have, let's say, a flapping route. If you had a flapping route in your IGP, then it would be very detrimental because the routers would spend the whole day reconfiguring or recalculating the best path. Another important thing about BGP is that it allows you now to have a policy for your network to control how you are reachable and be able to interconnect with other networks and things of that nature. It sets the administrative boundary for you. So just a quick look at the differences between interior and exterior. We have in interior, it's more trusting because it assumes you're within an administrative domain, right? That these routers are being managed by the same person. So they do have, they tend to have automatic neighbor discovery, which means if you configure that routing protocol and enable it on those interfaces, if it has another router on the other end speaking the same protocol on the corresponding interface, then they're likely to form a neighborship. So there's a lot of trust in that. Regardless of that trust, you should still set some passwords in order to ensure that only the authorized routers are able to form connections with one another. Then all the prefixes go to all the IGP routers. So all the IGP routers have the same view of the topology within that AS that they belong to. Unless there are things you can do to change that, but in general, they do have a same view of the topology. They know all the links that are currently up and how to get to them. Then it binds the routers in one AS together. Then for your exterior, you have to specifically, in most cases, configure your neighborship in BGP, right? If I'm forming I want to turn up a session with another autonomous system, or even within the same autonomous system, if I'm doing an interior BGP, I'll still have to specifically configure that router to form that neighborship and tell them, yes, you may connect to this particular neighbor on this IP address, which belongs to this particular autonomous system, in order for that session to come up. And then it sets the administrative boundaries, so you can easily tell where the role of one network ends and where the other start. And then obviously it binds the internet together. So that's how all the internet networks speak to one another on the internet to form what we know as the internet. So we said that for interior, we'll only carry our infrastructure addresses, nothing else. And then we want to keep it small, we want to keep it scalable and efficient. And for the exterior protocols, or rather for BGP, which is our only one, we want to carry our customer prefixes, our internet prefixes, anything that doesn't have to do with our own infrastructure, like how do I get to this POP or between this POP and that POP. You want to carry all of that, everything else, in your EGP. So this is just a simple diagram illustrating this. We have a network here, it's in an autonomous system, it's running BGP and OSPF or ISS. There's a link to an IXP. An IXP is an internet exchange point. We'll talk a bit more about that. But it's an internet exchange point where you can connect to other networks using BGP and be able to exchange some traffic there. Then you can have, if you have a customer who is maybe just only connected to your network only, they could use a static route. Like we said, there's no use having the full routing table if you're only going out one interface. Or if they have maybe more than one provider, which is called like multi-homing, then in that case, you would want to probably use BGP to connect to your customer. Then you definitely have to use BGP to connect to any other operator who's outside your autonomous system. You must never do OSPF with anyone who is not in your autonomous system. Like I mentioned, the different administrative distances, like these are the sort of like the priority, what makes this route more preferred than the other. And as you can see, they vary between the vendors. So no need to spend too much time here. They do vary, but we know that the connected interface will always be 0, which means it's very much preferred. And every other thing can be a different number depending on which vendor you're using, but the lower the number, the more preferred the lower the administrative distance, the more preferred that route will be. So if I receive the same route in OSPF, and say I was running OSPF and ISS, and I receive the same route and I'm on a Cisco, if it's exact same prefix, I will prefer the route from OSPF because it has a lower administrative distance. It means I prefer that over a route I would learn over ISIS. So that's what the administrative distances are used to decide what are the best routes, which ones are the ones that make it into our global RIB. All right, and that's the routing basics. Do we have any questions?
We have a shy crowd. Still no questions.
Okay, I hope I'm not going too fast.
No, I think you're going fine. I think you're going fine.
Okay, cool. Okay, fine. Let's go into BGP. Maybe we'll get a couple more questions there. Okay, cool. So let's go into BGP. As usual, we'd like to acknowledge Philip and the SRC team and the rest of his partners for developing and maintaining these materials. You can get more information from the NSRC website, as well as Philip's bgpforall.com. You're able to access various materials for internet technologies and service provider networks, peering, transit, and the like, right? So Okay, border gateway protocol. We've spoken about BGP. We have an idea of what it is. We know it's the external gateway protocol that exists right now. It's what we use to interconnect different autonomous systems. And that it allows us to do some policy within our network. So we've already said that the autonomous system is a cornerstone of the BGP. You're not able to do BGP if you don't use an autonomous system. And we'll get into the types of autonomous systems and all of that. So there are a couple of RFCs which can give you more details about BGP. It's been extended multiple times. It's a very robust protocol. It supports a lot of different topologies and use cases. So I would recommend looking up the RFCs. The RFCs are requests for comment, and you can find them on the IETF website where they standardize these protocols. And you can have more information about the actual deployment and design of BGP, as well as other use cases and best practices. So BGP is path vector protocol. And then it has incremental updates, like I said, so it doesn't continuously have updates just for the sake of having keeper lives. It'll do incremental updates whenever there's an update to be shared, and then gives you many options for policy enforcement, and allows classless inter-domain routing, which is just as a change from previous, probably many of you might not remember that when we had the class A, class B, class C IP addresses, and classless interdomain routing allowed for those bigger classes like class A for them to be broken down into smaller chunks, regardless of their initial class. So a class A network, which was ideally up to /8, I believe, you could break it down to a /24 or less, and the router would still be able to understand it, and etc. And so BGP is widely used for the internet backbone and requires an autonomous system. So what do we mean by BGP is like a path vector protocol? It's a path vector protocol because it defines how, it defines the route to your destinations based on certain attributes. And one of those attributes is AS path. We've already talked about how key an autonomous system number is in BGP. So this is an example of a BGP. So now you can see it. Yes, so this is an example of a BGP entry in a routing table. This is what you would see if you said show IP BGP. It's one of the things you would see. You would see a prefix. Oops, sorry. You'd see a prefix. You'd see the next hop. I forget what this is. Might be the weight. No, this is the autonomous system. Yes. And then this is the AS path. So this is who has announced the prefix to you. Sorry, it's a snippet of it. So we'll see it better in detail later. And then you will see the AS path. So you can tell which networks this prefix was announced to before it got to you, right? What's the path this traffic would take to get back to the destination? Like we said, traffic flows in the opposite direction of the announcement. So in this case, whoever announced this prefix is 11.268. This was a network that put this prefix into the BGP, and they shared this prefix with their upstream or their neighbor, who was 63.37, who then shared it with, announced it to 70.18, who then announced it to 64. 61, and now we are getting this announcement from 10.21, right? So you're able to tell how the traffic will flow to the destination, which is quite useful, especially because when you want to troubleshoot, you have an idea of where to check or who is responsible for what, and then you're able to interact with the right person about the right problem. So this is just a visual representation of the same. We have AS6461. Making an announcement. So based on that BGP entry that we looked at just now, then we're able to see that AS6461 would be able to send traffic back to AS 11.268 using the same neighbors that 64, 61 unticked from, right? So you get traffic information in one direction and you send the traffic in the other. So now we get to some definitions. We have transit. So already mentioned that transit is carrying traffic across your network, usually for a fee. Then you have peering. Peering is when exchanging information and traffic, usually for no fee. And you'll tend to see it happen between similar size networks. So two transit providers of a similar size might decide to peer, or in cases where it's not symmetrical traffic, you'll see probably with the content networks or content delivery networks, because generally the traffic will be heavier in one direction. Then there's a default we said is where you send traffic when there's no explicit match in the routing table. So we said the default free zone is made up of the internet routers, which have information about the whole internet. That's basically all that it means, that those routers have information about every single network that exists on the internet. Although that's transient, there's never all, because there'll always be an outage here and there, networks will go in and out. But in general, that's what it means. So we can take a look at how is peering and transit different, right? So here we have a couple of providers. We have provider A, B, C, D, E, and F. Let's assume these providers are in the same region. They're in the west of somewhere. So let's assume they're both in West Africa. So provider A and provider B are two maybe similar sized networks in West Africa. And there's an internet exchange point there that they happen to be members of. So they can decide, let's share some of this traffic here because we don't have to pay each other to exchange this traffic. We'll let the traffic flow over our networks and use our backbones, but we're not going to charge each other a fee. So that's peering. Then with transit, the only way for provider A to get to, provider E would be to use backbone transit provider who is present both in the west, and let's assume provider E and F are in the east. So backbone provider C has built a network that goes from west to east. So it's able to offer some services for those people who want to get connected between those two regions, right? So the backbone service provider is able to offer a transit service, which he will charge provider A for, and maybe even potentially provider E could also be his customer. So he could get paid times two, be very happy, build his network, and and then be able to charge for that. And in turn, backbone provider C could have another similar sized competitor who is also present in the west and has built out their network all the way to the east. So the two of them could say, okay, let's peer, because I know I have customer A and customer E, but I know you have B and F. So if we peer, it's possible that I can also save some of this capacity on this other link or this other one by being directly connected to you and maybe utilizing your backbone in some cases. And you can also utilize my backbone when you want to get to provider C, A, and E. That's why it's important for like the networks to be kind of similar size, so it's mutually beneficial. That's one of the key things about transit. It tends to be mutually beneficial for both of the networks that are connecting to one another.
Michelle?
So we have, sorry?
Yeah, Michelle, I just wanted to, bring your attention to the time. We have, it's okay. But we do have a question in the chat box.
Okay.
Yes. So there's a question from Kyle that says, how do routers connected by IGP determine the best way to route traffic to another AS if there are multiple border routers? And he further says, do the routers connected by IGP share knowledge of any prefix learned via EBGP?
Okay, yes, so there's, that's a good question that you've asked. So in IBGP, you would have to have a full mesh. All the routers in the autonomous system would either have to have a full mesh, meaning you make a peer session to each and every router that exists in the network, except yourself, obviously. So you make a connection to each of the routers, and then that tends to be quite cumbersome. So there are other technologies that you can use in order to avoid this. You can do something called, you can use a root reflector, because in IGP, okay, so for the loop prevention mechanism in BGP is that you must never see your AS in an update that you're receiving from someone else, right? Because you are the owner of your AS. You are connected to all those things. So you don't want to hear about it from someone else, right? That wouldn't be a very trustworthy update, or there might have been a loop. So the reason why in IBGP you're not able to announce a route you've learned from another IBGP speaker is that you could be creating a routing loop. So either each of the speakers directly tell one another everything that they know, such that in the end, each router has a full view of what all other routers know, or you could use a root reflector, which then breaks this rule and says that, okay, all these, in a good example here, we have this diagram. We can assume in this diagram, say that the router at the center can be a root reflector. So we can have all these other IBGP speakers making just a single connection to this root reflector, which might be also connected, since these are speaking eBGP, all of them. So they can all connect to the root reflector, and the root reflector is not allowed to tell another IBGP speaker about a route or an update it received from another IBGP speaker, but only to its clients. So you'd make routers, let's say 1, 2, 3, and 4 clients of this root reflector, which then is able to break the rule and announce IBGP routes to either IBGP speakers in the network. So it is possible. They simply just either announce all the routes they've learned to each other, or announce them to a root reflector, which is then able to pass on the information across the network. I hope that was clear.
Yes. So what I'd say would do is maybe you can just wrap it up and just give us 3 main points of BGP, because it's a huge topic, and I don't think we have enough time for you to go through all of it. So if you could just give us 3 main points of BGP, yeah.
Okay, so I give one good point. We talked about the loop detection and how that, so you should not see an update which has your AS in the path coming to you from another neighbor. Another good thing we can look at, and how does the BGP process contribute to the folder? Once we have some prefixes that we've received coming to our BGP process, so everything comes in. And once it's in the process we said has policies. So those policies we can either accept or discard a certain update. And based on what we accepted on our in process, we build that into the own rib for B. So that's in the BGP table. And then out of the best ones, evaluated by the root, all the routing, from all the routing protocols, those enter the global in the forwarding table. And the same goes used to announce out. You might receive a lot of information from your other peers or your customers, and you should send it out to this particular neighbor. You will have some policies which BGP will evaluate one by one based in the order of which they're written. So evaluate each and every one of the policies that you've come up with, and we'll go into that another time. Be able to determine, okay, these are the best paths, and the best paths are usually also BGP cannot announce a path that is not in its routing table. So it's not going to tell other people about a path it's not even happy to use on its own network. So only paths that exist in the routing table have the potential to even be sent out at all, to even be evaluated for being sent out, right? I think I would end it there. And we can find another time to carry on, I guess, and and complete the rest of the program with the BGP, then the MPLS as well. Is there any last questions maybe before we close, or something you'd like us to cover next time that you feel wasn't clear? Please feel free to put it in the chat, and then we can ensure that in our next fundamental series, we do cover that in depth for you.
Well, there's no other question in the chat box, but maybe in a minute you can just give an advice quickly to anybody that would want to enter into the engineering field, how to go about it, any advice in a minute. That way we can get on to draw.
I think the good thing about networking and all of that is that there's so much information available. I think I'll just switch off my video. My network seems unstable.
Yeah.
Yes, there's a lot of information online. Like I mentioned, I've just mentioned the resource right now from where I got these materials as well, which we've used for very many workshops. bgpforall.com has a lot of resources. If you're just starting out and you want it laid out for you nicely and clearly with some examples, I think that's a good place to start. I think another important thing that you need to do as a network engineer is you have to deeply understand not just how your vendor has deployed the protocol, but how the protocol is actually designed to work. So you can know when something's wrong or when your vendor has done something wrong, and you're able to troubleshoot better as things go on. So I would recommend also reading the RFCs. There've been a couple mentioned in the slides. Reading the RFC helps you understand how the protocol is designed, how it's supposed to work, and how to tell when it's not working. So you can tell this hasn't been deployed properly, or I'm not doing something correctly. But it gives you the in-depth knowledge about everything you need to know, regardless of whichever vendor you'll end up using at the end of the day. You'll have enough information to adapt to that. And I would say be involved in the community, coming for these sessions. And feel free, if you want to be the presenter next time, please put up your hand. We'll be so happy to have you. Be involved, share what you know. It helps you know more. That's what I would recommend. Be involved, be interested, and you'll get far.
Thank you so much. Be involved. Thank you so much, Michelle. For anybody that wants to know more, you can contact Michelle. Michelle, feel free to drop your email in the chat box. That way they can contact you as well.
Sure.
Yeah. And Abiola, thank you. We've noted your question. She wanted to learn more about RAV reflectors, but we do not have, time is against us. So unfortunately.
I'm glad to hear what people want to learn about.
Yes, exactly. We can note that down for next time. Yes.
Exactly.
So thank you so much. So now to the fun part. I'll introduce Alex from SMT to give us a quick overview of the late course.
Absolutely. So my name is Alex. I work for Systems and Network Training, who do all of the LINX courses for you guys, the LINX Accredited Internet Technician series. A lot of what Michelle's just covered are covered in those courses, just in a lot more depth. And I'm just going to sort of quickly run through a couple of slides just to give you a little bit of a feel for what we're going over. I mean, firstly, I just wanted to say sort of thank you for having us, and yeah, good luck in the raffle. You know, I hope that whoever wins it is, you know, gets the best out of it. And yeah, really looking forward to seeing who we can get on our courses. But right, so I'll start off by sharing my screen here. There we go, share. So we've been working with LINX for sort of the last 20 years or so. And what we've done is we've developed a series of 3 courses that essentially give delegates a chance to, or give network professionals a chance to start with the basics of networking and then progress to the point where they are able to work with networks and troubleshooting, configuring, setting up everything that you need to do with networking. Once you complete these courses, you should be able to really. So the 3 courses that they consist of are the first, which is LINX 1, which is the course that you guys have all been entered into the raffle for attending this call. So that covers things like mainly around TCP/IP, things like the 7-layer model, cabling, switching, and sort of looking at what's going on the wire. So using tools like Wireshark to analyze that. So that really gives you the grounding across all of it. The second course is LINX 2, which is all around, takes a much more in-depth look at the routing side of things. So looking at protocols like ISIS, OSPF, VLANs, and sort of covering things like subnetting and static routing as well. Lastly, we have what we've been going over with Michelle, BGP and peering. So that will cover all of that, as well as giving a light overview around topics like MPLS, COS and NAT. The idea behind all these courses is that it gives you the firm ability to use the knowledge to build your own networks and look after your own networks, but then also you can take that knowledge and apply it to topics like network security, network automation, telecoms over IP, just to sort of really give you a full overview and a chance to specialize a bit more going from there. All of the courses are 5 days in duration, so you know I really admire Michelle trying to cover as many topics as she did within the time that she did. It was very impressive. I think that, you know, if some of those topics really caught your attention and you wanted a deeper look at them, then this is a really good way to go about that. With regards to attendance, so the way that we're delivering those mostly at the moment is virtually, so no matter where you are in the world, you know, you can attend via a Zoom link. We are starting to reintroduce classroom-based training again as well, but obviously while we've got restrictions in place, we are trying to be mindful of who can attend. So, you know, if you need to attend virtually, that's always an option. So the way that we do our training specifically, and why we've been working with LINX, why we're trusted, is because we take a generic approach to technology training. So whilst you can take courses through Juniper and Cisco, and they'll give you a great grounding in how to use their kit, their switches, their routers. We're teaching more to RFCs, which again, Michelle mentioned there. So really covering the technologies behind those switches and routers. So, you know, what it does really is it complements that product training, gives you the greater understanding of, you know, how the technologies work behind the kit itself, and so it gives you the basis. That generic approach gives you the basis for anything to do with TCP/IP, automation, session initiation protocols, SIP, network time protocol, NTP, things like that. So really giving you a full view on everything that you need, and having that generic approach. You know, if you were to come on our courses and you didn't have the vendor specific knowledge coming into that, you could then go and apply that knowledge to whichever vendor you're working with. So, you know, flexibility really is the key with these courses. And whilst we do use a lot of Cisco kit for the courses, you know, it does allow us to, you know, if you are a Juniper house, for example, you know, we can adapt the course to that as well. So, you know, whatever your needs are, our specialists allows us to tailor that for, you know, whatever kit you're working with. So I'm just going to provide you a little view of sort of what's covered in the Lay 1 course. So I'm sure to a lot of you this all makes sense, but just to give you a little bit of an understanding. So what we have here is essentially everything that's covered. So we've got a switch here. We've got all of the end systems, so the PCs. We've got the wires here. We've got Wireshark monitoring what's happening on the wires using port mirroring, and we've got the packet with the MAC addresses on here as well. So it's a very brief overview of what you'll be covering on 5 days in just this one slide. But what it does give you is it gives you an idea of how much is covered through that generic approach. So where in a product specific course, you would be covering, you know, how the switch worked, and this being a Cisco switch. In our courses, it would be every part of the routing process, every part of the switching process. So, you know, everything that you need to then go off and network engineer your socks off. So what we want to do, well, what we are doing is offering a place on one of these courses to you guys as part of your attendance. And yeah, it will really give you a good grounding in the knowledge that you need to work as a network engineer. If you are already familiar with a lot of the basics that I've discussed in this slide, then obviously our Lay 2 course, our Lay 3 course, they're aimed at much higher level network engineers. And once you pass all those courses as well, doing the exams at the end of each one, you'll become a London Internet Exchange accredited internet technician, which is quite a nice title to sort of, you know, say that you've got put that on your CV or tell your boss, and you know, it's something quite nice and impressive to have there, and gives you a lot of flexibility in the working world and just within your organization in terms of what you can work with. Whether it's just yourself or an organization, you know, we do courses for groups as well as individuals. So feel free to come on our website, have a look and see what we have to offer. But, you know, there's a reason that we've been the trusted partner for LINX for their training for so many years, and, you know, I'm sure many years to come. And that's because, you know, we know that there's a good quality in what we do, and a lot of LINX partners come to us for this training. So yeah, if there's any questions that you have or any further information you'd like around our courses, then please feel free to get in touch, and be more than happy to enlighten you and see how we can help.
Thank you so much, Alex. Thank you. You heard him. Contact them. Yeah, so the lucky winner will be randomly selected and an email will be sent to you directly after this session. At this point, we'd like to say thank you so much. Thank you for everyone that stayed to the end to participate. We could not have done it without you. If you have not already registered for the second session, please do. It's in the chat box at the moment. The next session will be on data center operations and engineering. All you need to know about the ins and outs of data centers. This will be presented by Peering and Interconnect Specialists at Terraco Data Environments, Yolandi Robinson. She'll take you through the fundamentals and the technical aspects of racking, stacking, and patching, and some of the fascinating insights into Africa's most interconnected data centers. So please register, not only to be part of the draw, but also to enjoy and be educated next week. So without any further ado, thank you so much, and enjoy the rest of the day. Thank you, guys.